Here we are again, and we've given you the problem of the ants, and now we would like to show you the solution. The answer is that the ants meet in 12 seconds. And how are we to understand this? Well, let's go to the board. The ants are 12 inches apart from here to here, and he's going at 12 inches per second, but while he's walking, this one is also walking this way. So his path has got to swivel around this way, and likewise, because this one is going like so, etc., they are all sort of converging in some kind of spiral pattern, like so. But it is interesting to notice that at all times, due to the complete symmetry of the situation, the ants are always located on the four corners of a square. And the square is simply shrinking. So if we assume the ants to be on a round turntable, pivoted about the center, and simply rotated the turntable so that the square just shrank, then the fact that this ant was going on a curved path wouldn't make any difference to what this ant was doing, would it? Or another way of looking at it is consider a frame of reference. You see, here's how we'll maybe do it. Take a frame of reference where we are stationary with respect to this ant. In other words, just focus on this ant from above and rotate things so that this ant is always coming down there at a straight line. And in that frame of reference, whatever all these other ants are doing, this one is just moving down at 12 inches per second. By sliding around and rotating the table at the same time, we can keep this ant stationary, and we can keep this angle constant. And then it would be 12 seconds. I don't know if this is a very convincing analysis. I'm not all that thrilled with it. One slightly disquieting aspect of this problem is if you try and analyze how many times they spiral around and around before they finally meet. Well, let's just take it at the situation we've stopped them over here, and the square which originally had this guy in the top left-hand corner, now he's down here, so he's moved around about 90 degrees from his original angle, so we've had a quarter turn. But despite the fact that we've come a substantial distance while making a quarter turn, in reality, are we any closer to meeting than when we started out? Because, except for a change in scale, all we've really done is shrunk the original problem down to a smaller scale. But they're really, in some kind of cosmic sense, just as far from meeting as they ever were. So, although they do meet in a finite amount of time, 12 seconds, the number of spirals they execute, although they become tiny exceedingly fast, they do execute an infinite number of spirals. And that is enough of that problem. Let's clear the board. And move on to our topic for today. And our topic for today is, well, you see, to tell you the truth, I haven't really been all that prepared over the last week. Well, there's been this and that happening, and I had a lot of different kind of topics, and I still didn't choose one. But here's a fantastic topic, which is solving equations. This is the topic I love. This is a topic I haven't really worked at it seriously for about 2 years because I've been taking courses part-time at university since I worked there, and I took a course in quantum mechanics that was a heck of a lot of work, and that was a year ago. And And then this year I took a course in partial differential equations, and that has also sort of occupied my math thinking time. But I keep coming back to this problem, fantastic problem, solving equations. And here's how it goes. We know that the quadratic equation, x squared plus, let's say, x squared plus 3x minus 5 equals 0, has a solution which we learned in grade 12 that you take combinations of the coefficients and you got your minus b plus or minus the square root of this and that and a lot of crazy things. And those are supposed to be the solutions of this equation. And what it means is there's a certain number, and we call the number alpha. And it's hard to find alpha, but if we find it, then we put it into this equation, and we say alpha squared plus 3 alpha, take away 5, and we calculate them out, and it comes to 0. Now, remarkable as this is, it is true that for alpha there must be another number, totally different number, called beta. And beta has the same basic property as alpha. If we take beta and put it into the equation, we also get 0. The properties of alpha and beta are in some way indistinguishable from each other because they're not rational numbers. They are not numbers which can be expressed as a fraction like 27 over 13, which is one way we can name numbers and say this is a number. It's a kind of a number that we can only express in terms of how it relates to an equation. And it's a number which can only be expressed in terms of what happens when you square it and do stuff like that to it. And for any equation that's sort of like this, it is always true that alpha and beta are of the form a rational number plus the square root of a rational number. If alpha is a plus the square root of b, then beta will be a minus the square root of b. And just as I said, alpha and beta are not readily distinguishable from each other in their properties, in the same way these two expressions are not all that easily distinguishable from each other. It's most clearly seen if beta is a negative number. For example, if b was the square root of minus 1, well, let's put numbers to them all. Why not? Let's see. 3 plus I, 3 minus I. 3 minus the square root of minus 1. In the complex plane, we would represent these numbers 3 units on the real axis, 1 unit on the complex axis, plus or minus. The two roots we would say are complex conjugates of each other, and anyone who's done any work in math with complex numbers knows that it's very hard to tell the complex conjugates of each other apart, because the only thing that defines the square root of minus 1 is the fact that when you square it, you get minus 1. So to talk about the positive square root or the negative square root of minus 1 is almost meaningless. It's a funny thing that's not so well recognized that even if this is a positive number, and let me take square root of 2 as an example, that if you have an equation, quadratic equation, and the two solutions are 3 plus root 2 and 3 minus root of 2, we can draw them in the complex plane, and this time we don't really need complex numbers to draw them, because both of these values exist as numerical things on the real axis. This one is approximately 1.59 something, and this one is approximately 4.41 something. And so we think they're different numbers. We can tell them apart because, I mean, one is bigger than the other. They're completely different numbers. But bigness or smallness is sort of an extraneous parameter or quality that really has no business intruding on the question of expressions like this in terms of their properties. In a way very much similar to what we had in the case of complex conjugates. These two expressions, 3 plus root 2 and 3 minus root 2, in terms of their purely algebraic properties, are just as indistinguishable as these complex conjugates were, even though they appear to be different on account of their size. There is nothing you can say in an algebraic kind of framework about this expression which is not equally true of its brother expression, and I think this is really because of the indistinguishability of the two square roots of 2, positive and negative. We're not really permitted to say that one is the positive and we agree on this one and the other is the negative one, if we're strictly talking about their algebraic properties. And what I'd like to do is extend some of these ideas into the case of the cubic equation, the third degree equation, and see how they might suggest things about the nature of the solutions we should look for of a cubic equation. We said that a quadratic equation should have the form of a rational number plus the square root of a rational number. And it is totally fitting that this should be the case because the square root of a rational number is an ambiguous quantity which can take on either of two values. And two values is exactly what is needed to satisfy this equation. Because it's quadratic, there must be two solutions. Now, if we took an example of a third degree equation, x cubed plus x plus 1 equals 0, we should hope that a formula which would give solutions to this equation does the same thing that the quadratic formula does, in which in that it creates three possible choices of, in this case, two choices of the square root, give us two solutions. Let's see what we can do with the cubic equation. We might look at the solution of the quadratic equation and guess that a cubic equation should have a cube root. So let us try for solutions. Things like a rational number plus the cube root of a rational number, a plus b to the 1/3. And if we try this and try and patch expressions like this back into our original formula to see if we can make them null out to 0, you jerk around with the coefficients and you sort of find out that it's not going to work. Equation of this type, or a formula of this type, is not sufficiently powerful to plug into this formula and make all things cancel out and come to 0. And what you're then motivated to do, since this one is too weak, we got to try and find a way of making the formula more powerful. And I would like to propose one possible extension, and it goes like this. You take the kind of formula you had for the quadratic equation, and let's take it right here as it is. A plus the square root of b. Let's take that whole thing, take the cube root of it, and maybe add something for good measure, another rational number. So here's a complicated looking expression, which has got square roots of this and cube roots of that. And I would suggest that this expression might be powerful enough to give solutions to a cubic equation. But you get into a terrible problem with this formula, and I'll try and show you how it goes. We had, from this inner formula, two choices for the square root of b. And we'll call them, making the positive choice, a plus the square root of b, call it the positive choice. We'll call that one p. Let's take the whole cube root already. The cube root of this, we'll call it p. And the one where you had the minus square root of b, we'll take the cube root of that and call it q. Now, just the same way that taking the square root of thing, there's two possible choices for the square root. When you take a cube root of something, there's three possible choices for the cube root. I'm going to call them p, omega times p, and omega squared times p. And I'll show you where that omega comes from. It comes from, yow, bump my knee. We go back to the complex plane, 1, I. This is 1, this is minus 1. Minus 1 is the square root of 1. If we look for cube roots of 1 in the complex plane, we find them equally spaced at 60-degree angles, north and south of the real axis, at a value 1/2 plus root 3 over 2i, something like that. We call this one omega, and this one is the square of omega, omega squared. These are the three cube roots of unity. And if you look at any number like the cube root of 7, and you think of that as something 2 point something, then it is also true that omega times the cube root of 7 is also a cube root of 7, because cube root of 7, okay, omega times the cube root of 7 is also a cube root of 7, because when you cube it, this thing cubed gives you 7, and omega cubed gives you 1. So there's always 3 cube roots. Lost my microphone. The 3 cube roots of the p expression, p, omega p, and omega squared p. 3 cube roots of the cube expression, of q expression, q, omega q, and omega squared q. We've written a formula which we hoped would be capable of solving a third-degree equation. But when we started evaluating the expression, we find that it is so ambiguous that it generates a multitude of possible values based on 2 choices for the square root, 3 choices for the cube root. And here I've listed all the possible values that this formula assumes. Now, a cubic equation should have 3 solutions, but we've written a formula which gives 6 values. It's too many values. How can we write a formula and say it solves the equation and yet generate too many values that we would have to throw them away? And this is an incredible paradox, which almost seems to defy solution. And yet there is an actual way you get around this thing. You see, maybe you think the formula is too complicated, that we should have found a simpler formula, but if you try to make this formula any simpler than it is, you soon get into a situation where the formula is a little bit too simple, and you're playing around with the coefficients of the equation makes this fairly clear that you need a certain amount of complexity in the formula, but any time you add complexity by taking the square root of this, cube root of that, you unavoidably generate extraneous values. So how do you somehow write a formula which is powerful enough to solve the cubic equation, and at the same time doesn't generate too many extraneous values? And I think this is a topic that I'd like to leave for now and maybe come back to a little bit later. We should undoubtedly do a song, and because we always do a song on Math with Marty. Hear that amplifier turn on. What are we going to do, Neil? Did you think of one while I was doing all that math? No.
Out of hundreds.
A flat. Don't you think you should have called to tell me you were coming down? Girl, you look so out of place on this troubled side of town. It's a place where losers go when they know there's nothing left. And after losing you, I just lost will to live. Do you believe me now? I told you time and time again, my heart and soul is in your hands. Do you believe me now? Do you believe me now? Look at the living I've been through. I ain't nothing without you. Do you believe me now? Don't know why you changed your mind. I won't ask if this is real. I don't know if you're a dream. I only know how good it feels. If you could find it in your heart to say the fire for me still burns, I'd find a way to turn around down this road of no return. Do you believe me now? I told you time and time again, my heart and soul is in your hands. Do you believe me now? Do you believe me now? Look at the living I've been through. I ain't nothing without you. Do you believe me now? That's a beautiful song by Vern Gosdin from his album of a couple years ago, Chiseled in Stone. And what a good singer Vern Gosdin is. Speaking of good songs and good singers, if you happen to be catching Math with Marty on our regular Monday night time slot, don't turn off the TV after the show ends, because there's a dandy song that comes on right after our show, which is the black guys on the Caribbean thing. They got this song, Caribbean Man, or Caribbean Man. Fantastic song. I think this is born and bred on the Spanish Main. Caribbean Man, walked in sunshine and walked in rain. Caribbean Man. Well, you got to hear it. I mean, you'll listen to it when it comes on. It's an awesome song. And it just shows there's all different kinds of music that, you know, and isn't it something that we all have all different kinds of music. And we are drawing near the end of the show. And I got this problem, which I'm obviously going to have to return to some other time. Incredible fact that a formula powerful enough to have even the capability of generating solutions to a cubic equation seems unavoidably to sprout too many heads. I mean, it grows up too many solutions. You've got a square root in it and you've got the cube root. Right away, you've got 2 choices for the square root, 3 choices for the cube root. And, you know, so there's 6 values that the equation can assume, and yet it must satisfy, it's supposed to generate the roots of a cubic equation which only has 3 roots. So how do you overcome this paradox? And I think we'll talk about that another time. It is one of my favorite topics. And we should just hit the road with some powerful music here. And what do we got? Let's do I heard about it from a friend of mine. Hey, he lives across the county line, the sweetest grape that ever grew on the vine. And now I think about her all the time. Her daddy Robert and her mama Lou, they had a daughter they named Bobby Sue. And now she's 18 and she knows the truth. Nobody's gonna tell her what to do. Bobby Sue, can't you see my love's true? I wanna marry you.